Welcome to the deep dive. We take your sources, unpack them, and pull out the key insights, all for you. Today, we're digging into something that's kind of like the hidden engine behind almost all the AI you see around you. It's an algorithm called backpropagation. It's absolutely crucial, but it's history. It's long, it's surprisingly twisty, and honestly, often completely overlooked. So our mission here is to trace that journey. We want you to understand not just what it is, but also why its bumpy road from being ignored to driving the deep learning revolution is, well, a really powerful lesson in how breakthroughs actually happen. Now, to really get why backpropagation was so important, we kind of have to go back to the early days of AI and understand the big challenges they were facing. Think 1950s, 1960s, there was this massive excitement, right? Around early neural networks. Frank Rosenblatt's perceptron was the big thing, a single layer network. And people thought, wow, this is it. It's going to learn, make decisions, maybe even translate languages. The hopes were just sky high for what these, artificial neurons could do.
Yeah, but that optimism, it crashed head-on into a pretty solid wall. In 1969, Marvin Minsky and Seymour Papert published this book, Perceptrons. And it wasn't just like a casual critique. It was this really sharp mathematical takedown. It exposed the fundamental limits of those single-layer perceptrons. And the most famous example, the thing that really symbolized this limitation and kind of stopped things in their tracks, was the XOR problem. Mm-hmm. Imagine you've got points on a graph, right? Blue dots and red dots. And you need to draw one single straight line to separate them. Well, the XOR problem sets up the point so you just can't. There's no single line that works. And since perceptrons could only learn these simple linear boundaries, they couldn't solve XOR, which proved, basically, they couldn't handle lots of real-world problems that aren't so simple. Now, researchers knew, theoretically, that multi-layer perceptrons, MLPs, with more layers should be more powerful. They could solve problems like XOR. But they hit this massive snag. It's called the credit assignment problem. Think about it like a really complex machine, hundreds of gears inside. If the final output is wrong, how do you figure out which specific gear, way back in the middle, caused the error? And not just which one, but exactly how much to tweak it. For these multi-layer networks, there was just no good way, no effective algorithm to know how much each connection, each weight in those hidden layers contributed to the final error. So how could you possibly adjust them correctly? This failure to solve credit assignment, plus, let's be honest, some pretty overblown promises about AI, well, that led straight into the AI winter. We're talking early 70s through most of the 80s. Funding just vanished. Progress on neural networks ground to a halt. It wasn't just disappointment, it was a real technical dead end they'd hit.
Wow, that AI winter sounds brutal, a genuine roadblock for the whole field. And it really underscores how vital solving that credit assignment problem was. But you mentioned earlier, the answer was kind of already there.
Yeah, that's the astonishing part. The solution to this huge problem that actually existed for years, just hidden in plain sight. Backpropagation wasn't like one single aha moment. Its core ideas actually popped up independently in totally different fields, through different names, long before AI folks latched onto it. It's a classic case of, siloed knowledge.
Absolutely right. If you zoom out, the basic ideas go way back, to the 1960s, actually. In control theory, you had researchers like Henry Kelly, Arthur Bryson, Stuart Dreyfus. They were working on optimizing complex systems like multi-stage processes. How do you control something with lots of steps in the best possible way? And their methods involved applying the chain rule from calculus, repeatedly, but backwards through the system's steps, conceptually. That's identical to what backpropagation does, calculating efficiently how each part influences the final result. Then, fast forward to 1970, there's this brilliant Finnish master's student, Seppo Lineenana. He formally published a generalized version of this backward calculation method, called it the reverse mode of automatic differentiation, or AD. But here's the kicker. His work had nothing to do with neural nets. Zero. He saw it as a really efficient way to calculate derivative rates of change for any complicated function you could define in a computer program. Think about that. This general-purpose tool for understanding complex systems was just out there, waiting. The first person to actually connect the dots, to explicitly say, hey, we could use this backward error thing to train neural networks, was Paul Werbos. It was in his 1974 PhD thesis at Harvard. He laid it all out, but it was mostly ignored. His thesis committee was apparently a bit skeptical, and more importantly, the timing was terrible. AI was deep in the AI winter. Nobody was receptive to neural network research, especially not something that looked computationally heavy back then. So is the solution basically waiting for its problem, or at least waiting for people to be willing to listen to the solution for that problem?
That is just incredible. The answer to AI's biggest hurdle, the credit assignment problem, was right there for over a decade. But stuck in different silos, control theory, automatic differentiation, maybe even mislabeled, you could say, for its AI potential, just waiting for the right context, the right moment. So when it finally blew up in 1986, it wasn't really about inventing something new. It was more about translating and showing this existing idea worked to an audience that was finally ready, right? Which brings us neatly to 1986, a really pivotal year. Backpropagation finally steps into the spotlight. It was this paper, Learning Representations by Backpropagating Errors, by David Rimmelhart, Jeffrey Hinton, and Ronald Williams. And its huge impact wasn't because the math was brand new, we just established it wasn't. It was about the demonstration, powerful experiments. They showed clearly that neural networks with these hidden layers could actually learn meaningful stuff on their own, extract useful features from raw data. Internal representations, they called it. They could solve problems previously thought impossible for NNNs, and that demonstration. That's what really started to thaw the AI winter for neural nets. Sparked a whole new wave of optimism.
Exactly. And to see how it did that, let's quickly break down how backpropagation actually works. It's basically a two-step dance. First, the forward pass. Input data say an image goes into the network. It travels forward, layer by layer. Each neuron does its calculation, applies an activation function, passes the result on, until you get a final output at the end, like the network says cat. Okay, second step, error calculation. You compare the network's output cat with the correct answer. Maybe it was actually a dog. You use a loss function to measure how wrong the network was. Gives you a single number representing the total error. Then comes the crucial part, the backward pass. This is where the magic happens. This solves credit assignment, that error signal. It travels backward through the network, from the output layer, back through all the hidden layers. Using the chain rule, it efficiently figures out precisely how much each individual connection, each weight, contributed to that final error. It's like tracing the error back to its sources. And finally, weight update. Now that you know who's responsible for the error and by how much, you adjust the weights, usually using an algorithm called gradient descent. You just nudge each weight slightly in the direction that reduces the overall error. Repeat this whole process many, many times with lots of data, and the network gradually learns to make better predictions.
Okay, that makes sense. It sounds like a solid mechanism, a solution to that big problem. So, if it was so great, why didn't neural networks just take over everything right then and there in the late 80s or early 90s?
This leads us to what some people call the AI autumn, right? Another cooling off period.
You're right. It wasn't immediate world domination. Far from it. Instead, through the 90s and early 2000s, another technique actually became much more popular. Support vector machines, or SVMs. And there were some very good reasons for that back then. First, training SVMs involves something called convex optimization. Think of finding the lowest point in a smooth bowl. There's only one bottom, and you're guaranteed to find it. That's the optimal solution. Simple, reliable. Neural networks, though, their loss surface, the landscape of possible solutions, is non-convex. It's bumpy, lots of little dips, local minima. Your training algorithm could easily get stuck in one of these shallow dips, thinking it found the best answer, when a much deeper, better valley existed somewhere else. This made training NNs feel a bit unreliable, very sensitive to how you started things off. Plus, SVMs had this clever trick for handling complex nonlinear data. The kernel trick. Imagine data points all mixed up on a flat sheet. The kernel trick is like mathematically folding that sheet in a really smart way, so suddenly the points become easily separable by a simple cut. And it did this without actually having to compute the complex coordinates in that higher dimensional folded space, which was often computationally cheaper and more robust than using multi-layer NNs, especially with the computing power and data sizes available then. So for practical purposes on smaller data sets, SVMs were just easier to work with, more robust, and often gave better results. Backpropagation's real power, its potential for deep networks, it was kind of put on hold, waiting for the rest of the world compute power data to catch up.
That's really interesting. So backprop solved the MLP credit problem, got us past single layers. But then, okay, what happened when people inevitably tried to build really deep networks? Like not just 2 or 3 hidden layers, but many more. Because you said another wall appeared, right? A problem that came directly from using backpropagation itself. Networks either learned incredibly slowly or just went haywire.
Exactly. That was the next major hurdle, the depth barrier. And it was formally identified and named the vanishing gradient problem by Sepp Hochreiter back in his 1991 thesis. Here's the issue. Remember that backward pass? The error signal travels back layer by layer. Well, at each layer, it gets multiplied by the derivative of that layer's activation function. The popular activation functions back then, like sigmoid or tan, have derivatives that are always less than or equal to 1, often much less than 1, actually. So as the error signal propagates backward through many layers, it's getting multiplied by these small numbers over and over again. What happens? It shrinks. exponentially. It vanishes. By the time the signal reaches the early layers of a deep network, it's become incredibly tiny, almost zero. So those early layers barely learn anything. They effectively stop updating. Your deep network isn't really learning deeply at all. And there's the flip side too, the exploding gradient problem. If for some reason, like large initial weights, those derivatives or the weights themselves are consistently greater than 1 during the backward pass, then the error signal gets multiplied by large numbers repeatedly. It blows up, becomes enormous. This leads to huge unstable weight updates. The network's learning goes completely off the rails. It diverges, can't learn anything useful. So yeah. Vanishing or exploding gradients both made training truly deep networks extremely difficult, practically impossible for a long time, which kept them from consistently beating methods like SVMs for years. It's kind of ironic, isn't it? The very mechanism, the chain rule that made backpropagation work in the first place, also created its biggest limitation when you tried to go really deep. It pointed towards needing more than just backprop alone.
Okay, this is where it gets really good, right?
Yeah.
Because the solution wasn't just one thing. You're saying it was like
Yeah.
3 different streams of innovation maturing all at once, finally breaking through that depth barrier and letting backpropagation really shine. This sounds like the moment things truly started to accelerate. What were these pillars?
Exactly. It wasn't just one fix. It was a convergence, a sort of virtuous cycle kicking off. Pillar number 1, parallel processing power, pure hardware muscle. This was the GPU revolution. Graphics processing units, GPUs, were originally for video games, right? Rendering complex scenes requires doing millions of simple calculations simultaneously, massively parallel. Around the late 2000s, people realized, hey, this parallel architecture is perfect for the matrix and vector math that dominates neural network training. NVIDIA's QD platform was key here. And the watershed moment was AlexNet in 2012. It won the big ImageNet competition by a huge margin. It was trained by Alex Kruszewski using 2 NVIDIA gaming GPUs, GTX 580s. It had something like 60 million parameters, way too big for CPUs at the time, or even one GPU. Training took about 5 or 6 days on those 2 GPUs. On a CPU, it would have taken months, maybe years. Impractical. AlexNet proved deep learning was feasible. It shifted the entire field towards using GPUs. That was massive. Pillar 2, data abundance. You need fuel for these big engines. Deep networks with millions of parameters are incredibly data hungry. Without tons of labeled examples, they just memorize the training data that's called overfitting and fail badly on new stuff. The crucial ingredient here was ImageNet. Started by Fei-Fei Li around 2006, it wasn't just big data. It was high-quality, human-verified data. Over 1 million images, labeled into more than 1,000 categories. ImageNet, especially through the annual ILS VRC competition, provided this challenging standard benchmark. It drove competition, pushed innovation, and gave models like AlexNet the vast amount of data they desperately needed to actually learn effectively and show off their power. And Pillar 3, algorithmic ingenuity. Smarter software tricks. Hardware and data weren't quite enough on their own. We needed ways to directly tackle those gradient problems. A huge one was changing the activation function, moving away from sigmoid and tan, which squashed the signal, to the rectify linear unit, or VLU, simple function. If the input is positive, output the input. If negative, output 0, max 0x. Why was this great? Because for positive inputs, its derivative is exactly 1, constant, no vanishing. So the error signal could flow back through many layers without shrinking. It acted like a much better conduit for learning in deep nets. AlexNet used ReLUs, and it trained much faster because of them. Then, better ways to just start the network. Weight initialization. Remember, bad starting weights could cause exploding or vanishing gradients too. Glorot, or Xavier initialization, around 2010, looked at how many connections go into and out of a neuron and set initial weights to keep the signal variance roughly constant across layers. Worked well for functions like Dan. Later, He initialization 2015 was developed specifically for ReLU. Since ReLU kills half the signal, the negative part, He initialization compensates, keeping the signal strong even in very, very deep ReLU networks. Essential stuff. And finally, managing overfitting in these giant models. Dropout. Introduced by Hinton and his team around 2012, as models got huge, memorizing the training data was a massive risk. Dropout's trick is clever. During training, you randomly just switch off or drop a fraction of the neurons in each layer for each training example. It's like forcing the network to learn with different subsets of its neurons all the time. It prevents any single neuron from becoming too specialized or dependent on others. This forces the network to learn more robust, redundant features. It improves generalization, how well the model performs on new data. It's never seen significantly. AlexNet also used dropout heavily.
Wow. Okay, so putting it all together, it wasn't just one thing. The deep learning revolution, it wasn't a single invention. It was this Synergy, this virtuous cycle, GPUs providing the power, ImageNet providing the fuel, and then these clever algorithmic fixes like ReLU, better initialization, and dropout solving the inherent problems of deep backpropagation. They all came together at the right time, they amplified each other. AlexNet wasn't just a great model, it was like the first time all these necessary ingredients were combined perfectly in one recipe, showing everyone what was now possible.
That's a perfect summary. Backpropagation's journey is, well, it's pretty amazing when you lay it out. Started as this obscure math concept, ignored for ages, finally popularized, then revealed deeper challenges, and only reached its true potential when all these other pieces, hardware, massive data, clever algorithms fell into place around it. It really is the workhorse of deep learning today. But yeah, definitely not a magic bullet. Its success is totally tied to this whole supporting ecosystem.
And looking ahead, backpropagation is still absolutely central. It trains almost everything, from the CNNs doing image recognition to the transformers powering large language models. But it's not the final word. There are challenges, like it's not very biologically plausible, right? Our brains probably don't work exactly like that, with such precise error signals going backward, which is fueling a lot of interesting research into alternative ways networks might learn, maybe more like how we do. And maybe here's a final thought for you to chew on. That AI winter we talked about. It's a really potent reminder. Even with all the incredible buzz around generative AI today, there could still be a gap between the hype and the reality down the road. Maybe new bottlenecks we haven't hit yet could lead to disappointment, funding shifts, who knows? So what does this history tell us about the next big leap in AI? Maybe it won't be some radically new invention from scratch. Maybe, just like backpropagation, it's an existing theoretical idea, perhaps already out there in some niche field, just waiting for its own convergence moment. The right hardware, the right data, the right algorithmic tweaks to finally unlock its full potential and change everything all over again. Something to mull over until our next deep dive.